What I want to show you here in this video is the autofocus algorithm that we're working with. Actually, I have read a few papers that I found online and that I am uploading to GitHub so that you can read them just download them. And from there I found that there are good results among the papers, and some of them have these algorithms that I'm going to show you. The first one, actually I'm going to show you that in the log at Hackaday that I'm doing. Let's first start with an introduction with this. Basically, when you want to find the focus in an image, you basically have pretend that you have a very focused image with a lot of detail. That means that you have high frequencies and low frequencies in the same picture. And so whenever you have a blur image, but you still have some detail about the image, that means that you have the low frequencies. Because you have used a low pass filter so that the edges in your image just disappeared. And that's what we want to do in this autofocus, and that's what several papers do. And there are also other statistical methods that work just fine. But in this video, I'm going to show you just 3 of them that I consider to be the best one. So as I was telling you, these methods based on detecting edges, sharpness in the image, or using statistical methods to measure the variance among the pixels. Okay. So from what I'm going to show you, let's first see some notation. And so M represents the number of rows in the image, and N represents the number of calls in the image, and mu means the mean of the image. Okay. So the first algorithm that I have seen is the normalized variance. This is a statistical algorithm, and basically, as you can see, it's just finding the variance just roughly in the image, so that you have all the pixels in the image that you extract it. You subtract its mean, then you power it to the 2, and then you divide that between the number of rows times the number of calls and times the mean, and then you have a value. Okay. So let's start first with this method. And so I have done a very simple program in Python to show you this. So I just prepared this, and I'm going to show you the image that we're going to see. So let's move that here, and we're going to do frame that is equal to cv2 dot imread, and we're going to read image 0 dot jpg and cv2 dot imshow in the window I, and we're going to put the frame. Okay. And so from there we just do this wait key, and this is the image that we're going to see. Okay, this is one of the images that we have taken with the automatic digital microscope, and as you can see, this is the best focus that we can acquire with our microscope. You have to remember that the microscope that we are using is one that we have taken from an old hospital, and they don't use it anymore at Cobija. So I just want to emphasize that we want to show that with our devices we can make diagnostics even with this old equipment that hospitals don't use it anymore. So we have acquired this image, as you can see right here. As you can see, this patient has a lot of infection, so and that's gonna be the topic of another video. But this is the image that we're going to work with the autofocus. Okay. So we just read the image that I have shown you. We extract the rows and the columns, and then we're going to add some noise to the image, and I'm going to show you that in just a few seconds. So I'm using where are those functions? I'm using a cv2.blur image, which basically makes an average of a set of pixels in the image. So if you add an average of 5 times 5, then you have a more blurred image, but you can still see everything that happens there. Then we have a nice noise too, with a larger kernel, just per se, and that's going to make the image even more blurred, and with 20, with 40, with 500 matrix, and one with 10K kernel. So this is going to make the image extremely not it's going to eliminate all the high frequencies, so you will have a very blurred image. Okay, so these are the images that we obtained from those functions, and then I'm going to use these three functions that I have made to make things easier. So we're going to start with the gate variance, as I said. We're going to send the frame and all the noised images that we have acquired here, and we're going to measure the variance. Okay, so this is the function that measures the variance in the image. So as you can see, I'm using NumPy in order to make things even better. Here's the power 2 and the frame minus the frame, the mean of the frame. Okay, and of course that the function that I have showed you is called from another one. One thing that I have to mention before we start is that the images that we are using are being converted to grayscale, so that we don't have to deal with three-dimensional spaces. Besides that, color doesn't seem to help very much whenever we're making this, so it's better to just have a grayscale image, and we can still get a good measure of the focus. Okay, so from there we just use the matplotlib library in order to make the plots, and I guess that's it. Then I'm going to show you the curve of the values that we obtained whenever we're making the measure of the noise of not the noise, the autofocus. I mean the focus image. We're going to obtain values, as you can see from the bar. We're going to calculate the variance of the whole image, and then we're going to return a value. And as I have told you, this problem is reduced to finding the global maximum of the whole function that we are going to create, measuring with the algorithm the focus of each image. Okay, so we're going to take the original frame, and we're going to measure its variance, and we're going to take the noise frame, and we're going to measure its variance, and so on, and each one is going to have a value. Now, as you will see, and actually I will run this to make things easier to explain, that is going to, the more focused image is going to show you the highest value, while the less focused images are going to show you a very small value, as you will see. And so, as I was saying, the problem reduces to finding the global maximum. Okay, so I don't know why this is being displayed like this. I don't know why, but as you can see, come on. Okay, this is the original image, the one that I have shown you. This has more blur, more blurred, extremely blurred, more and more blurred, and here it is completely blurred. It's actually all white. And just for you to believe me, I'm going to show you this, but using the imp show from OpenCV, because I checked this and I don't know why this happens, and I don't have the time to solve this. So I just know that it is working, because if I display this in the OpenCV, then I have a more blurred image than this. And besides that, the curve that I'm going to show you just fits well with what I was telling you. Okay, so this is the frame that is in focus, and as you can see, it has a value for more or less of 16.70781, and the next one has a value that is smaller, but not that much, as you can see here. So from what I want to tell you, from the experience that I have had, you can still have some degree of I mean, making the classifier is going to work even if we use this image or this image. These two are acceptable. Even this one is acceptable, because anyways we're going to use a low pass filter to eliminate high frequencies and make whether the color detection algorithm or the machine learning algorithm more reliable, so that we don't have that much variance in the image. Okay, and as you can see, the more blurred the image has, the more smaller the value from the algorithm that returns is. And as you can see, the more blurred image from here that I'm going to show you in just a minute has the lowest value. Okay, and so this is the curve from the variance algorithm. So I'm going to close this, and I'm going to make a very quick show OpenCV. I'm going to make a very quick thing that so that I can show you that this is working, and show OpenCV. Okay, and okay, so this is the image that I was trying to show you. This is the more blurred image, and as you can see, you can see nothing here compared to this one. And that's the interesting thing, because as you can see, the original frame is this one. More noise, more noise, more noise, more noise, more noise, more noise, and this is the most blurred image. This is the one that you can see nothing. And this is actually what happens whenever you are trying to focus an image. You start with normally this, and you move here and so on until you get to this very high resolution image. Okay, and man, we'll have to close this all manually, so I guess I'm just make this the quicker I can, as quick as I can. And then we're going to pass to the energy of the Laplace algorithm that is going to measure the what happened, that's going to measure the focus of the image. And basically what you have to do is that you need to find the second derivative of the image, and by that you have to convolve the whole image with this kernel that you can see over here. So you convolve the image, and after that you need to find the power of the function. So you sum up all the pixels in the image, and then you power it to the 2. And that's what I'm going to show you right now. And as I'm making the right modifications here, just I want to tell you that the Laplacian, the energy of the Laplace is the one that has the best results, I think, for me. So some papers say that you need to find the algorithm that suits better for your image, because you're going to have images that have high density background, low density background, and that's going to be another feature that you have to check whenever you're making an autofocus algorithm. Okay, but I have seen so far that the energy of the Laplace seems to be a very good approach to finding what I want. And so let's see this. Let's move to the to the get Laplacian, and so it's going to compute the same thing that I have shown you before. We're going to see the whole images, and then we're going to see the curve of the noised images. Okay, so there is an error here. Okay, so as I was saying, the energy of the Laplace seems to give the best results because of the variability that you have from the highest value in the curve and the lowest value of the curve. So I like that very much, because I can have a very differentiated approximation, and so it's best for my results, as you will see. And it's easier to compute this kind of stuff. I don't like being stuck at local maximum, so this is going to fit very well to my purpose. And as you can see, the most focused image has a value of close to 60. The next one that is not that focused has a value of what does it say, 4, and the other one has another 4, and so on. So it goes down. So this is the curve that we obtain from this. And finally, we're just going to see quickly, because I didn't find this to be very useful because it takes a lot of time, the Brenner gradient. Okay, so this is a fast edge detector, and as I have told you at the beginning of the video, this tries to some of the algorithms want to find edges want to find the edges in the image. So this is basically what it does. And as you can see, you just calculate the power of the image, but without using the power 2, and No, actually, you don't calculate the power of the image. You just take a pixel by pixel, and then you subtract it from a pixel that is m spaces away from this pixel. Okay, and that's going to find an edge, as you know, because edges have very similar values whenever there is I mean, they have a different value, and that means that we have an edge. Okay, so that's why we're subtracting this, and we have this power to the 2. So there's something wrong here. This 2 shouldn't be here. It actually should be here, so be careful with that, and I'm going to show you this. Okay, so let's go and comment this, and no, I don't want to do that, and let's start this. Okay, so as this is computing and I have showed you the results, I know that you say, if you know about autofocus, you say, oh, but you should take a lot of images because there are local maxima, and we haven't seen any local maxima. And you said that there were going to be local maxima, and there is a reason why I'm not making a more extensive plot. And the reason is that we have seen that whenever we're focusing the microscope, the actual focus is just a few millimeters from the starting point of the z-axis. That means we just go straight up until the slide kind of touches the objective, and then we just move down one or 2 millimeters, and there is always the focus point. And so, why don't we take advantage of that instead of taking a lot of processing time with our embedded system, or trying to adding an algorithm that finds the local maximum, which kind of takes a while. So why don't we take this assumption, and so we get a faster algorithm, because we know where the focus point is almost always. Okay, so there is some variability, but it's so little that we can assume that it is from 1 to 2 millimeters behind the starting point. So if you, I don't know, you have seen the videos about the automatic digital microscope, but in the z-axis we have added a button. So whenever the z-axis goes up, it gets to a point where it touches the sensor, and the sensor tells that it is the home starting point for the z-axis. So we know where that is. We have calculated it with a vernier. So from there we just have to go down 1 or 2 millimeters, and from there we have a not so huge function to calculate our focus. We have a very reduced one, and as you can see, it reduces to finding the maximum at 8 or 10 points, and that's more than enough for an exhaustive search algorithm, for the British Museum algorithm. So you know that it doesn't get very complicated until you get to the 10,000 values. So just getting from 10 to 30 values is just enough for finding the autofocus. And okay, this algorithm just takes a while. The computer is not that fast, but I just wanted to explain that. And as you will see, it works very well. And we'll go with that. Now there is something very wrong with the project, and it is the fact that, for example, the image that we're using right here, we took that image but with a borrowed ocular. That wasn't ours. The one that we have has a lot of dust, and due to the dust, when we cleaned it, we just made scratches on the mirror. I mean on the lens, on the lenses, and now our image is not that good. But it doesn't matter for the classification or the segmentation algorithms. It's not very deterministic. I mean, we can still make even the color algorithm work very well, but for the human side, it is kind of annoying to look at that. It looks ugly, but luckily the machine doesn't care about that, and she can just predict as good as it does with a clean and new lens. Okay, so I guess that's going to be a a good point, because it means that we can still work with equipment that has a lot of scratches. And come on, it takes so much time. I just can't believe this takes so much time. I guess this is because of the... oh my god, I have so many pythons. Maybe that's why. Okay, so it had finally... I just made this work, eliminating the whole pythons, and this is the result that we have. As you can see, these are the images that I have showed you before, and this is the result that we have. So the focused image still has a very high value, while the other not so focused images and the not focused image at all has a very low value. What I don't like about this is the fact that it takes a lot of time and it computes very high values. I know that I can still divide this, but the algorithm just takes too much time. Actually, I haven't seen the complexity of the algorithm. We should use big O notation to make this work, and I don't know why it takes so much time. It is just O n times m, and that's 300, 7,200 pixels, so it's not that much, but still we just have very good values with the variance. And it's of course faster than this algorithm, so we're going to take that algorithm. So that's it for the video, and goodbye.